carbon-oxygen bond, this is negative and this is positive, and these are, they don't have much electronegativity at all. So there's a net polarity to the entire molecule because this polarity of this bond is not canceled out by anything. So this is a polar compound. It's not as polar as water though. See, water, here's water. I have water in each of these burettes. I have each of these pure liquids. So in this burette, and the reason I have it in the burette is I'm going to use the Stopcock to make a fine stream of the liquid, and then I'm going to see how it reacts to an electrostatic charge. You know, I was telling you the Greeks discovered that if you rub amber with wool, you got an electrical charge. Well, I've got a piece of wool, I've got a piece of plastic, little black plastic here. And if I rub wool with plastic, it turns out it puts a negative charge on this piece of plastic. And because acetone, for example, is polar, it has a negative end and a positive end. So if I bring this negative charge up to the stream of acetone, it should bend the stream because it would be attracted. The positive end of the acetone would be attracted to the negative end of this rod. And you'll see that happen. It also was learned later on. It took, I guess, quite a while. Benjamin Franklin, you know, the statesman, he's on what, the $5 bill, but he was never a president. He was a statesman. He was a diplomat. But if you rub silk with a glass rod, it turns out the glass rod gets a positive charge. And it was Benjamin Franklin that discovered that there were two kinds of charges, positive and negative. Well, see, if you have a polar compound, it has a negative and a positive end, so it should be attracted to either kind of electricity. The negative end of the acetone would be attracted to a positive charge. The positive end would be attracted to a negative charge. And likewise with any other of the compounds that are polar or not polar. Okay, so what it takes to be polar is to have polar bonds, but it also takes something else. The polarity must not cancel out. So it turns out water is actually also polar. Water is a pure molecule of two hydrogens with an oxygen. The oxygen is most electronegative, so it's very polar. In fact, water is more polar than acetone. Acetone is polar, but water is more polar. This is more polar. And it has a higher dipole moment. But this compound, even though each of these carbon-chlorine bonds, each of them are polar, each bond is polar, these two polarities cancel those two polarities out just because of the geometry. So I have also in this other burette, I have some carbon tetrachloride, which is here's my model of it. And you can see, you can't tell because it's a three-dimensional model, but these two polarities, they're very polar, very polar. All of these bonds are very polar, but these two actually geometrically cancel those two. So that the whole molecule has zero polarity at all. And so it will not be attracted to either the positively charged electricity or the negatively charged electricity. So I've got all these three burettes filled with these three liquids. I've got the compound sitting next to the liquid that's in that compound. This is liquid water. This is liquid carbon tet. And this is liquid acetone.
Water in each of the burettes?
No, I didn't say that. I just got through saying that water is in this burette. This burette has carbon tetrachloride, which is also a liquid compound, and this has liquid acetone. The three burettes are filled with three entirely different compounds, the models of which are in front of the burettes in which they contain. And what we're going to be investigating is how the stream, I'm going to let a stream of each of these compounds out the bottom of the burette, and then I'm going to see if it's attracted to an electrical charge, which I create by static electricity. It's called static electricity. If you rub plastic, which is the R equivalent of amber, with wool, you're going to get a charge on this plastic rod. And I've got a little device here, and you can see what it consists of. It's this metal ball connected by a metal rod through a rubber stopper down to two metal, you see those two aluminum metal leaves in there? So it turns out this thing is called an electroscope. The electroscope. So I built this little electroscope because it helps detect whether I have an electrical charge or not.
So we put that as material, but you wanted to put glass stopper.
No, it's called an electroscope. Call it an electroscope. I'm just telling you what it's made out of. This electroscope, watch now. If I take this plastic rod and I rub it with the wool, it's going to create an electrostatic charge on here. And if I touch it, you might want to get up out of your seat and come over here where we're doing the experiment. If I touch this charged up rod to that electroscope, look what happens. Can you see when I touch it there? What happens is the negative charge on the plastic rod travels down the metal. Remember, metals are good conductors of electricity. It goes down the metal rod and hits each of those little leaves. And because I'm putting the same charge on each of those leaves, like charges repel, so the charges repel one another.
Like in
and so the leaves go away from one another. And so it's a way, this little device was invented to determine whether you have an electrical charge. Now look, the electrical charge, I don't even have to touch it. Look, I just wave near it. And I'm not Harry Potter.
Oh, and that thing moves.
See there, I'm not Harry Potter. Because there's an electrical field coming off of there. Huh?
What would you call that thing in there that's moving?
This is the whole device is called an electroscope. Those are called metal leaves, aluminum leaves. But that device is used to determine if you have an electrical charge. So I only bring this into view so you can see that I have a way of testing whether I have an electrical charge or not. Now I've already got a negative charge on that electroscope. So if I take my glass rod, remember I said when this was first discovered, you know that the ancient Greeks discovered static electricity, and that's where we got our word electron. Remember I told you from the Greek word electron, which means amber. They named it after amber, the plastic petrified tree sap that they messed with. They didn't have plastic. But it turns out they called the kind of electricity you get from that amber-like material, they call that resinous. And they call the kind you get with glass vitreous, because the word vitreous means glassy. But it took Benjamin Franklin to determine that one of the charges was positive and one's negative. The negative charge, like on the rubber or the plastic, is negative. But if you rub silk onto glass, this becomes positive and this becomes negative. So look, if the humidity isn't too high, I might be able to get this to work. Well, it shouldn't be doing that. What's going on?
It's all in there.
Let me try charging that up again with my negative charge. the kind of electricity I'm generating is called static. You know, like rubbing your feet against your carpet and then touching the doorknob, you get a little shock. It's just called static electricity. So I'm using that to charge up those leaves, and I was hoping that I could demonstrate that if I bring up the opposite charge, it should collapse, but it's not working today for some reason. Anyway, there's an electrical charge in either case, you can see that. It did move it, yes. Okay, so here's what I'm going to do. I don't know if I'll use both. Maybe I'll use both rods to show for water, but I don't have to use it for all. Water is the most polar. Then acetone is polar, but not as polar as water. And then carbon tetrachloride, I said, because of its shape, is a totally nonpolar compound. So when I bring, watch this. When I bring this charge, I'm going to prove I have a charge in each case with my electroscope. Okay, so if I rub the static electricity onto the plastic rod and prove there's a charge, and if I make by the way, you can do this at home if you want to amuse your children or your nephew or whatever. You could make a fine stream of just tap water. Just make a fine stream, and then take a balloon and blow it up and rub it in your hair. And if you bring that charged balloon up to the water, it will divert that stream of water. If you have a fine enough stream, if you have it too cool, real hard, it's not going to divert it. If you have a fine stream, it will divert it. You can amaze and get something going on. Watch this now. I'm going to make a fine stream of water. Okay, so here goes, the fine little stream. Watch this. Charge up the rod. Bring it to, see there, look.
Oh, man.
It's attracted because the reason that happens is this is negatively charged, right? And water, it has a polarity. This end of the water is slightly negative, and this end is slightly positive. So, the positive end of the water molecule is actually attracted to the negative charges on this rod. But now, because it's polar, let me show you this. I can take the same water. If you haven't caught on to what equipment I've got these stands holding the 3 burettes, and in each of the 3 burettes I have a sample of each of the pure compounds. I have pure liquid distilled water, I have pure liquid carbon tetrachloride, and I have pure liquid acetone. And the only reason I put them in these devices is so I can make a fine stream. I've got these little beakers down here to catch the stuff that's running off. So they're just there to catch that. And I made these models of the compound so that you can visualize what I'm working with. Alright, so if I take the same water and I rub the glass rod with silk, I should still be able to divert, to make the stream bend toward the rod, because you see, it would be the negative end of the water that will be attracted to the positive glass rod. So if I do this, watch now. If I take the same stream of water and I get my charge going, whoops, and if I get my charge going here, you see, doesn't matter whether it's positive or negative, because it's polar. It has a negative end. That's what the word polar means. Polar has nothing to do with a cold bear that's white colored. It's not that kind of pole. It's an electrical pole. You know, in magnetism we have a north pole and a south pole, but in electricity we could have a negative pole and a positive pole. And that's why we call it polar. Water is polar. And I was telling you, acetone is also polar. But carbon tetrachloride, even though it consists of polar bonds, is a totally nonpolar molecule because the polarities cancel one another out geometrically. Not the even number, that's not the reason. The reason is the shape. And so, this even though this experiment is very simple, it is showing you something at the molecular level, right here, with the simplicity of this experiment. You're seeing the difference in the actual shape of the molecule affecting, that's an A, the polarity. If the geometry makes the polar bonds cancel one another, it'll be a totally nonpolar compound. So I have picked carbon tetrachloride as my totally nonpolar compound. So when I make my stream of carbon tetrachloride come out of the burette, and I picked the burette to just so I could have a little stream, a little fine stream, then well, nothing should happen in this case. So nothing happening is not a big exciting thing to see, but you see, I can't divert the rod at all, and yet look, I do have electricity and nothing. And the reason for that is, although each one of these carbon-chlorine bonds is polar, these two form a vector polarity that cancels this vector exactly. And so it's totally, it consists of polar bonds, but it's totally nonpolar. This is from the chapter we talked about. Remember we talked about structure and polarity? So this is right from there. And so that one doesn't divert, isn't attracted to the rod at all. And now it turns out, what did I say about acetone? This is acetone. It's
polar, but it's not as polar anymore.
Supposedly, it's polar, but not as polar as water. And the polarity is along here. You know, the geometry around this middle carbon is a trigonal plane because it's sp2 hybridized. And so the polarity is all right along here, and these bonds aren't very polar at all, so we can just ignore them. So what do you predict to happen if I bring the charged rod up to the stream of acetone, which is in this burette?
I think it'll go like, here's the rod, I think the water will be off from it. But not as much as the water? Yeah.
No, it would, if it's polar, it's got to be attracted.
Oh, okay.
But not as much, it won't veer off.
Maybe it won't bend as much.
Yeah.
Is what we might predict.
Yeah.
Okay, let's see what happens. Remember in the first experiment we ever did together?
What happened water?
We boiled water. Remember we boiled water, but we boiled it with ice.
Yeah.
And we had to come up with an explanation as to why when I keep adding the ice, does the water boil at a lower and lower temperature? It's because it is getting a lower and lower pressure. So, because that's astounding. That's something you don't think is going to happen, but it happens. And that's what we do in science. When we find a phenomenon and something happens to our surprise, we have to somehow explain it. So I'm going to surprise you right now. Let me take my stream of acetone and try seeing what happens with it. So here's my acetone in this other burette. That feels a little loose. Okay, so here's my stream of acetone. Bring up my charged up rod. And well, look, let me raise it a little higher. And stop it and start over. It's okay, I can pour the chemical back in because there's nothing in the beaker to begin with. So it's still pure acetone. So I'm going to try it again. I'm getting an actual charge, which I can prove with my electroscope. See, there's my charge. So when I open that stream, let's watch. Well, that seems to be diverting even further than the water. Look. Oh, isn't that just like I'm missing the rim? The stream missed the rim. It said, isn't that just like a guy? Just so you understand. You have to clean up around the side.
That's what happened when you're drunk.
No, it happens.
You missed the whole commode. Oh.
But now, we need to somehow explain why, although I said, you can take my word for it, acetone is less polar than water, it appears to divert. That is, the stream bends even harder, more exorbitantly with the less polar molecule. So we've got to come up with an explanation as to why that is. Do you understand what my query? Why, if acetone is not as polar, why is the stream of acetone diverting more than an equal stream of water? Well, I may be asking too much for you to figure that out because you may not know enough physics to figure that out. Did you ever study physics?
No.
Well, you've ever heard of the laws of motion?
Yes.
Newton's first law of motion is that a body at rest or in uniform motion will stay at rest or uniform motion unless forced to change. And a force comes from an acceleration. And acceleration is inversely proportional to mass. That's the second law. F equals ma is the equation. F, force, equals mass times acceleration. So acceleration equals force divided by mass. And acceleration is a change in velocity. Velocity is a change of position with time. So if you have, according to the first law, a stream of liquid falling, it's carrying its mass with it. And if you bring a force, like the electrical force, from these rods, they're going to be attracted, right? Then the stream will divert, and that's an acceleration. Because you can change the speed of your car with 3 different devices in your car. In other words, you have more than one accelerator. In your car, you have the accelerator. It's the vertical one on the right, and I wish some people would use it.
Or stay out the lane.
And then there's the other one that you get to slow down, right? That's called the brake. That's just an accelerator, but it's a decelerator. It slows you down. And then there's the steering wheel. Because see, you can change velocity, which is a vector, by changing either its magnitude, speed, or its direction. So if I turn the corner, even going at 5 miles an hour, and I stay at a steady 5 miles an hour, if I turn the corner, I'm also accelerating that car because I'm changing its direction. Well, when I change the direction of the flow of that water, I'm accelerating that flow of that liquid. So it turns out then, if what I'm saying is correct, the water, being more polar, should have a greater force of attraction to the plastic rod. And the acetone being less polar should have a less force, but despite that fact, the water diverted all right, but the acetone diverted more. So there has to be something going on here, algebraically, to compensate for what I'm saying. The amount of acceleration or the amount of bend, the amount of diversion is inversely proportional to mass. So, look, don't go away. What does this burette actually measure? It doesn't measure mass, does it? What does it measure?
Water.
No, what does it measure? What unit?
Volume.
It measures volume. So, this stream of liquid is carrying a mass per unit volume, right? So you've learned this in chemistry this semester, I hope. What do we call the measure that is determined by mass per unit volume? What do we call that? There's a name for mass divided by volume. What's the name of that? It's called density. That's exactly right. So we're not really looking at how much mass is coming out of this stream, but we're looking at the mass per unit volume coming out of there, aren't we? So what must be true if we compare the density of water to the density of acetone. Because see, even though the acetone is less polar than water, the stream of acetone is bent further by the plastic rod than the stream of water. So if we compared the density of water to the density of acetone, which one would be more dense? Water. Because I can only bend the stream a little bit, compared to the density of acetone, which I bend a whole lot, because its mass per unit volume is much less. It's a little lighter on its feet. And that is our explanation. Well, now look. How many of you know what the density of water is? All of you should know. We made an assumption in one of our last experiments when we were titrating vinegar versus ammonia. We made an assumption about the density of water. We said it was about how many grams per milliliter? How many grams per centiliter? Water. Isn't it? One? Yeah. The density of water is 1 gram per milliliter, or 1 gram per cubic centimeter, same thing. So we have to then, from this experiment, we have to then conclude that if we looked up the density of acetone, it would have to be less than 1. Isn't that our conclusion? Huh? That's our hypothesis.
Say that again?
If we looked up the density in the Handbook of Chemistry and Physics of acetone, which is, that's its common name, acetone. It's also known as dimethyl ketone, or its proper name is propanone. It has all those names. It has all these AKAs, also known as. So if I looked it up in the Handbook of Chemistry and Physics, it should come out less than the density of water, and that will prove our point. And it's kind of a what do I want to say? It's kind of a spin-off, an extra added feature of my little experiment here to show the difference between polarity and non-polarity is that we can also discover something not only at the molecular level about the polarity of these molecules, but even about their relative density. Okay. So, let's go in here.
What was the purpose of the lab?
Investigating,
Sure. Yeah. Or I put them on YouTube.
I put investigating how the stream is attracted to electric charge created by electricity.
Here is the Handbook of Chemistry and Physics.
Oh wow.
And it has all kinds of stuff in it. But one thing it has is physical constants of organic compounds. And acetone is an organic compound. And under acetone, if I look it up, I see that the density of acetone is 0.79, rounded off, 0.79 grams per milliliter. And 0.79 is less than 1. So, we proved our point.
Yes, sir.
Acetone really is less dense than 1. And that explains why I can bend it more easily, even with a lesser force. I can bend it, a stream of it more easily than I bend the stream of water. That has a greater force.
On the purpose, is it investigating how the streams are attracted to electrical charge created by
What our purpose is to investigate polar and nonpolar compounds. The spin-off of the experiment was that in doing so, we actually discovered something about the density of the two different polar compounds because of the way they behave with the charged rod. It's just a little extra added spin-off. Okay, so get your notes clear to yourselves.